Good afternoon. Welcome to my presentation entitled Comparison of Accuracy and Density of Static and Mobile Laser Scanners. My name is Maciej Trzeciak. I am a PhD student at the University of Cambridge, and Dr. Ioannis Brilakis is my supervisor. In this paper, we will explore and compare the performance of laser scanners and render it to different use cases popular in the construction industry. To begin with, we have different types of scanning devices in the construction industry. Some of them are presented in this slide. The first one is a static laser scanner. How they work is you place the device next to the object you want to scan, enter some settings, press a button, and depending on the settings, you wait around 10 or 30 minutes, you take out an SD card, plug it into your computer, process the raw 3D data, and you have a 3D scan. Then we have photogrammetry approaches, where you take a bunch of photos of an object from different points of view. You can attach a camera to a drone, for example, and take a lot of pictures. Then you transfer the images to your computer and use special software like the Bentley Context Capture, for example, to reconstruct the object in 3D. However, for these two approaches, the effort spent on acquiring and processing data grows significantly, as shown in this figure. And some of the reasons are that the devices are not mobile enough and cannot provide prompt feedback. The quick feedback on how well you reconstruct is quite important because often you collect a lot of data and it turns out that you cannot create point clouds out of it. So there is no guarantee that the collected data will give you the 3D model that you want. Therefore, the last couple of years brought a proliferation of mobile scanning solutions that can collect data quicker, hence leading to a lower operational costs. They are relatively newer, and especially lidar-based handheld scanners, so these two, seem to be the dominating solutions for outdoor mobile mapping in the construction industry. I will explain in a moment what lidars are, but one important consideration while picking a device for your purpose is the range at which the device operates. For example, the range of Google Tango is up to 7.5 meters. You can imagine scanning a big bridge with a device of such a range. It would be a nightmare. Therefore, the remaining two, lidar-based, are more applicable for our industry as the range is simply greater. Now, let's dive slightly deeper into how mobile lidar-based scanners work. I will skip how static scanners operate because they are way more known to the construction industry and they do not need much explanations. So let's see what a lidar is and how it works. A lidar is such a pack manufactured currently by many companies such as Velodyne and RoboSense, which gained popularity in the last 5 years, mainly due to the increasing interest in autonomous driving. LiDAR stands for light detection and ranging, and a LiDAR sensor shoots impulses of light using its, for example, 64 laser beams. So now we have 64 laser beams, and not only one, as it is the case for static scanners. Because this shooting is done very frequently and fast, it looks like there are beams rotating at high speed and they give us tons of instant depth measurements. Accordingly, the device works kind of like a radar. And now you can place such a LiDAR on your head, walk around the building, and as you go, a 3D model of the building is being created. And if someone is interested in how it is possible to incrementally build such a model, you can check a keyword SLAM, which stands for simultaneous localization and mapping. There are a couple of companies that utilize SLAM to provide professional mobile scanners to the market. Two of them are GeoSLAM with its ZEP horizon and Carta with its stencil tool shown here. Okay, we know how the static and mobile devices work. Now let's see how I measure accuracy in our paper. Imagine that I want to scan such a square target, which is very thin because it is simply a sheet of paper. I place my LiDAR on my desk, so the LiDAR is fully static, not moving, not using the SLAM technology, and I scan the whole scene. The result is such a point cloud. When we filter out the background and leave only one target, that will be the result, a small portion of the whole point cloud, which represents just the target. Now we know that our target in reality is very thin and flat, so we can fit a virtual plane to the point cloud. I have done this, and the process of fitting a plane to a planar target is described in our paper. We know that the target is very thin, but the point cloud is not. So we want to measure the spread of the point cloud. How do we do that? Well, we take, for example, this point, measure its distance from the digital plane, and then we take another point, measure its distance to the digital plane, and we do that for all the points. And now, when we kind of histogram all those distances, we receive such a distribution, which is, as we know, called a Gaussian distribution. It turns out that this distribution is fully described by two parameters. Its mean and standard deviation. The mean is, in this case, is 0 if we measure the distances in the coordinate system of this plane. And the standard deviation is equal to this formula, which is exactly the same as the standard deviation we were taught at statistics at college. We also remember from statistics that for a Gaussian distribution, plus minus 2 sigma covers 95% of the area of this distribution. That's why we call it a 95 percentile in the paper. In the context of the target, the percentile can be interpreted in such a way that the chance that any of these points lie within plus minus 2 sigma is 95%. Armed with this knowledge, we can now relate the standard deviation to guidance by RICS. RICS stand for Royal Institution of Chartered Surveyors in the UK, and they published the most general and internationally recognized guidance containing recommendations for specific professional tasks, seen in the last column. RICS defines a band table with accuracy recommended for different use cases, including engineering surveying, measured surveys, and many others. And here comes the thing. They define two standard deviations, so 2 sigma, as their measure of accuracy. In our paper, we adopt this definition of accuracy, and we will use it to measure the performance of the scanners and render it to the different use cases from this table. So to put all these pieces together, we will use 2 sigma to measure the accuracy of the point clouds representing the target. So what I did in my experiment was I took a planar rectangular target and placed it at the distance of 5 meters. I scanned the target with the static Faro scanner, then with a mobile GeoSLAM ZEP Horizon scanner, and then with the Carta Stencil 2 scanner. Then I moved the target from 5 meters to 10 meters, scanned again with all the scanners, and then again, I moved the target from 10 meters to 15 meters, scanned, and then I repeated these activities until I scanned the target at 40 meters. Afterwards, I processed all the produced raw point clouds in the respective software products, and then I post-processed and analyzed the point clouds in Cloud Compare. And here comes the table with qualitative results. The columns represent point clouds at a growing distance with an increment of 5 meters, and the rows are related to the devices, the Faro, GeoSLAM, and Carta scanners, respectively. And I think that the problem is clear here. For the static scanner, the shape of the point clouds at all the distances is relatively consistent. It is more or less a rectangle, whereas for the mobile laser scanners, the noise of the points grows along with the distance. It is the case for both of the tested mobile devices. I have illustrated this with these bounding boxes surrounding the point clouds. We can also notice that the scans in the last 2 rows become less and less recognizable along with the distance. In fact, from around the 20th meter, it is even hard to notice what the shape of the target is. I have further analyzed the results quantitatively and presented them in 3 graphs. Let's start with the density of the target, and then we will move on with the accuracy. In this graph, we can see that As the distance grows, the density of the target, measured in points per second on a logarithmic scale, decreases linearly or even slightly exponentially. So we can draw a conclusion that the density of the point cloud is an exponential function of the distance, because this linear decrease is on the logarithmic scale. While both mobile scanners produce a similar level of density across all the range, the static scanner has a worse performance on this score. However, this gap dilutes along with the distance, which would be even better pronounced on the linear scale. Now, moving on to the next graph, depth noise measures the accuracy along the axis perpendicular to the plane of the target. As we can see, it remains steady for the static scanner at the level of around 1 millimeter, while for mobile scanners, it is 20 to 30 times higher at 5 meters, and it gradually increases to reach about 40-50 times that value at 40 meters. It is also worth noting that this accuracy meets the requirements of use cases such as measured building surveys, topographic surveys, and low accuracy setting out, since it is lower than 50 millimeters along all the range for all the tested devices. And the previous graph illustrated the accuracy level measured in the direction perpendicular to the target. So what about the remaining two directions in our three-dimensional world? Well, the remaining part of the accuracy is shown in this graph. To be more precise, this graph shows how the accuracy changes in the plane of the target. So the previous graph showed the accuracy in the direction perpendicular to the target, and now we can see accuracy in the plane of the target. I slightly simplified this by measuring simply the area of a bounding box surrounding the point clouds. That orange dashed rectangles represent the bounding boxes, surrounding the point clouds, and whose area we can see in this graph. As we can see, initially a very small gap between the static and the mobile scanners very quickly grows along with the distance. This is quite interesting because it means that the initial difference at 5 meters is around 20 to 30%, whereas it grows to 100 or even 600% at 40 meters. This might bar the engineers from making precise measurements using point clouds needed for certain use cases, such as engineering surveying. This is the end of my experiments, and now I will present our conclusions. In this paper, we showed a simple though effective method for measuring the accuracy and density for static and mobile scanners. A rectangular target of known dimensions was systematically scanned by all the mapping devices at varying distances, and its point clouds were processed to collate their statistics. Our experiment showed that the density of the scanned targets measured in points per second decreases exponentially along with the growing distance to the target, and that the mobile scanners outperform the static mapping devices in this regard. The trend is opposite when it comes to accuracy. The static scanner produces scans that are at least 20 times less noisy than those by mobile devices, while the accuracy specifications for such use cases as measured building surveys, topographic surveys, and low accuracy setting out are met by all the devices almost at the whole range. The more demanding use cases, such as engineering surveying, could only be satisfied by the static scanner. We also conclude that the combined fact that the density and accuracy decrease along with the distance to the target heightens the problems in finding edges and corners in scans, forcing the user to guess their exact position. Finally, in this paper, we're investigating measuring accuracy and density using a target of known dimensions at a growing distance, which is one of many approaches to the accuracy measure. Our method, presented in this paper, although relatively simple, seems to be quite challenging, particularly for mobile mapping devices. On the final note, our research leading to this paper received funding from BP, GeoSLAM, Lying O'Rourke, Topcon, and Trimble. We would like to thank these companies for making this research possible. With that said, I would like to thank the audience for watching, and now I am happy to answer questions.